Okay. Back to this. Yeah. So if delta naught is less than P, so if it takes lesser energy to go to the next orbital, which is Eg, compared to pairing an electron, the electron is going to take the route of lesser energy. So this is going to go into the Eg orbital. So delta naught is less, matlab, in the case of weak ligands, you can be pretty sure that, yeah, it's going to go into Eg only always. Somewhere in the middle of this thing, you'll need to compare, okay, that particular metal atom ka pairing energy kitna hai, delta naught kitna hai. Like you need that information to figure that out. And if it's a strong ligand, yeah, like some of the strongest ligands, it will automatically, it's so high that it won't be able to cross the pairing energy. So the other way around, if delta naught is greater than P, so the Eg orbitals, delta naught is so high that Eg ka energy has gotten so high that it's just easier to first pair up the electrons. So in that case, pairing will start. So D4 will go into the T2G orbitals. Okay. So this is, let's write it properly. This will take place in the case of weak field ligands. And you will end up with high spin complexes. High spin because more number of unpaired electrons. So like plus half, plus half, plus half, plus half, like the spin just adds up. And if pairing takes place, so this will happen in the case of strong field ligands. And you will end up with low spin complexes because maximum have paired, so the spins like basically cancel themselves out. Lower number of unpaired electrons, the chances for diamagnetic or compounds with lower amount of magnetic moment is what you'll end up with in this case. Okay. So D4 onwards, yeah, D4, D5, D6, this is what will happen. In the case of, yeah, up to D7. So after D7, like whether it fills up T2G first or EG first, D8 and D9 cases are going to be the same thing anyway. Your end result will be the same thing. So for D4 to D7, this is the case. D8 is, yeah, you'll have low spin anyway. All of them will be paired up.
Yes, I didn't understand spin complexes.
So another name for coordinate compounds, we also call them complex compounds or complexes. So when we say high spin complex or low spin complex, you're looking at the number of unpaired electrons. Okay. So suppose, for example, if we are to fill D6, like 3D6 aa gaya, like electronic configuration. If we have to fill 6 electrons in D orbital, in case 1, where delta naught is less than P, so it's easier to go to the next orbital than it is to pair electrons. So you have 1, 2, 3. Fourth electron will go here. Fifth electron will go here. Then the sixth electron will go over here. Right? So here you have 4 unpaired electrons. So if you remember, the 2 electrons in the same orbital, they differ only by the spin number. Like they have equal but opposite spins. Right? Plus half, minus half. Remember that? Yeah. So in this case, these two will cancel out, plus half, minus half. But since all of them are unpaired, they're all spinning in the same direction. You have plus half, plus half, plus half, plus half.
But how do you know that delta naught is lesser than?
So that,
P.
yeah, that's why you look at what sort of a ligand it is, what metal atom it is.
So you've taken an example. Vaisa.
Yeah. So
So
case,
basically, when you have a weak field ligand, which means like I is a weak field ligand, right?
I minus.
I, yeah, I minus.
Hmm.
So if you have that, if you have like that is the approaching ligand, so then that like वो electron share करेगा Eg orbital से,
Yes.
like that.
Hmm.
So that implies that the delta naught is much lesser than pairing energy.
It doesn't imply, like, because I minus has a weak field, the delta naught happens to be less than P, which is why the electrons get filled in this way.
But pairing energy as in the energy required to pair two electrons in a particular orbital, right?
Yeah.
So how is that related to the approaching ligand?
So that, no, approaching ligand will decide delta naught. Pairing electron, like pairing energy, is for the particular metal atom.
Also, how is pairing energy related to spin complex?
So that's what, like, look at case 2, you'll understand it. Okay, so case 2, if delta naught is higher, so D1, D2, D3 get filled up. D4 कहाँ पे जाएगा? Pairing energy
It
is
will pair with the,
yeah, because delta naught is high, मतलब Eg orbitals बहुत दूर है, higher energy. So it's easier for the electron to pair क्योंकि pairing energy is lower. So it will go here. Then D5 will go here. D6 will go here. Okay. So यहाँ पे we end up with 0 unpaired electrons.
Can you explain this case again?
What part of this cover?
How the electrons are being filled? I don't understand.
So that depends on the energy. So delta naught is splitting energy, just decided by the ligand, strong field or weak field. Agar strong field hai, तो delta naught will be pretty high, like it will split them right up. If it is a weak field, the delta naught will be lower, pretty much. If not exactly equal, they'll be like almost at that this thing, which is where your pairing energy comes into picture. Pairing energy is the energy required to pair up an electron. So अगर weak field ligand है, तो delta naught is low, like it's easier to reach the Eg orbitals than it is to pair an electron in the same orbital. So that's why D1, D2, D3 के बाद D4 is going to go into Eg orbital. So D5 will fill again equal energy. And then क्योंकि सारे orbitals fill हो गए, then D6 will go and pair with this. It will try to minimize pairing because pairing has higher energy.
I didn't understand.
What exactly did you not understand, Kaveri?
This like if it's strong field, then there is higher delta naught that I understood, and then it will be harder to. After that, what you said, I didn't get like about the EG.
So delta naught will be higher. Delta naught is splitting energy, right? Like the difference in energy between T2G and EG. Remember? T2G
Yeah.
इधर है, EG इधर है. So it's कितना difference है? This is delta naught. So if delta naught is low, it is lower than pairing energy. मतलब difference इतना ज़्यादा नहीं है, छोटा ही है. So electrons, it is easy for the electron to exist in the Eg orbital than it is to go pair with another electron.
What will be filled first, T2G or EG?
Pehle T2G, lower thing. So I'm talking about D, like the fourth electron. Where should it go? Yeah. So pehle first three T2G, it will fill that. Then the fourth electron will depend. See, D4 to D7 is what we are talking about. D1, D2, D3 तो T2G में ही जाएगा. D4 कहाँ जाएगा? So that depends on how high is Like, what is the energy difference? Is it easier for the electron to go into Eg, or is it easier for it to pair? तो अगर Eg का energy बहुत ज़्यादा, if it is very high, where it is greater than the pairing energy, it will prefer to start pairing up the electrons. If it is low enough, pairing energy ज़्यादा है, so it will prefer not pairing. It will want to go in the lower energy route, so it will go into Eg. So high spin, low spin comes from this fact. Lots of unpaired electrons, high spin. Here, all the spins are getting cancelled out, so you have a low spin complex. Yeah.
But isn't this against that?
Yeah,
What was
exactly.
that? Hund's
Rule.
multiplier rule.
Yeah, which is why, no, we are still following Hund's rule. So what you studied there was independent metal atom, जिसमें all the d orbitals have equal energy. They'll start filling up one by one. But this is happening only in a specific case when there's a ligand approaching the metal atom, and इसीलिए तो like energy has increased for two of the d orbitals, right? It's not equal anymore. So the electron is still following key, it wants to fill up the lowest energy possible. It's just figuring out which one is lower. So if this difference is pretty high, it's still going into the lower energy orbitals, which happens to be T2G. But if it is like low enough, then it's still following the original plan of filling up the d orbitals and then coming back and pairing.
Still, it will be against Hund's rule, right? Like the
It's not.
all of them will first.
Hund's rule, like it states that pairing up takes place once all the orbitals of equal energy are half filled.
Oh, equal energy.
Yeah. That's why you fill up S first and then you go to the higher energy ones. Here, instead of treating all 5 d orbitals as equal, think of it as these 3 are one set and then these 2 are another set. Hare, you were about to ask something?
I forgot. But
Okay. Smera, any questions? No?
oh yeah. Sorry. We say that delta naught is lesser than pairing energy, so high spin complex. So like high spin is because ki a key there'll be like only one of them will cancel out, otherwise there is spin in each of them, whereas in case 2 the like every like it's getting cancelled out, so there's no like spin left. Vesa, right?
Yeah. So this we discussed last class also. So high spin complexes are characterized by more number of unpaired electrons and they usually tend to be paramagnetic. Low spin complexes are characterized by like if not fully paired, like maximum, there'll be a maximum number of paired electrons rather than unpaired, and they tend to be diamagnetic. Even if they are not diamagnetic, they have extremely low magnetic moments, plus lower number of unpaired electrons. Okay, so this is this thing. Another fun fact, it has been observed that D4 to D7, like complexes just may the configuration you have 3D4 to 3D7, they are more stable for strong field than they are for weak field.
Could you go back to the previous?
Yeah. Kaveri, if you finished, switch to the next one.
Miss, what did you that example 3D6 is for what?
Oh, like for example, if we were to figure out what will happen in the case of 3D6 configuration, like कोई भी metal like cobalt, iron जो भी है, iron 2 plus, cobalt 3 plus जो भी है, if it has a 3D6 configuration, how are the electrons going to be filled?
Acha.
So specifically, like we discussed a couple of examples, you have cobalt forming complex with ammonia and fluoride. You have CONH3 taken 6 times, you have COF6. So one of them, like fluoride, we've seen is weak field. You end up with a high spin complex. Ammonia is on the stronger side. You end up with a low spin complex in that case. Let me know when you're done. Like I can take up that example. Kaveri? Kaveri?
Yes, ma'am.
Huh. Okay. Yeah, generally like D4 to D7 configurations may, like suppose you have metals that are in D4 to D7 configurations, you have more stable complexes for strong field than for weak field. So for example, if I have CO NH3 take NH3 taken 6 times, 3 plus, and CO F6 3 minus. Okay. So even though like oxidation state of cobalt is same in both these cases, this may be cobalt is showing +3, this may be cobalt is showing +3. It is observed that this is diamagnetic, this is paramagnetic. Why?
Is it because in case of what is the first compound name again? Sorry.
Name is,
Cobalt.
so this, okay.
Yeah. Okay. The first compound basically has NH3 group. So that is a stronger ligand, which is why it will have lesser unpaired electrons, and that is why it will be diamagnetic.
Yes. So this forms a low spin complex. It's a stronger ligand. And fluoride F minus that you find here is a weaker ligand, forms a high spin complex. Okay. So Smera, if you recall, when we were doing VBT, we needed to know the magnetic moment first to figure out what would be the shape and electronic configuration and all of that. But with
Yeah.
CFT, yeah, you just look at, okay, what is the metal, what is the ligand, and you can predict all of these properties. So that's a major
Same example we did na, in BBT.
Yeah. I took those examples only, see, like so that you get to see how we can apply these principles and get a better idea with CFT. So let me know once you've written this down. So then we'll now move on to tetrahedral complexes. So once you guys got the hang of this, tetrahedral is pretty easy because everything remains the same, strong field, weak field. There's only minor differences because the shape is different. Everything else will remain the same.
Miss, I didn't understand coordination number.
Coordination, what?
Number.
It's just how many bonds or linkages that central metal atom has. So CONH3,
So, like, other than the coordination bond included, all of them.
no, only the coordinate.
Then
Only the like CONH3 6 है ना? So cobalt has 6 coordinate bonds with 6 ammonia ligands. So iska coordination number is 6.
But what if in a particular compound, not all of them are coordinate bonds? Then how would you know if?
So apart from coordinate bonds, what other type of bonds are metals capable of forming?
Ionic.
Ionic, right? But ionic is not exactly, it's not a geometrical bond the way covalent bonds or coordinate bonds are. Ionic bond just happens to be that you have oppositely charged species and they're attracted to each other. Okay.
Yeah.
So we don't count the number of ionic bonds in that case. Like we only count the number of coordinate bonds.
No, like for example, NH4. Oh, sorry. NH4OH. It has a coordinate bond. It has covalent bond as well as ionic bond, right? So, in that case, how would you because I know it has only one coordinate bond, I'll say coordination number is 1, but
No,
otherwise, how would you
yes,
figure
no,
out?
we don't. That's not coordination number. Like this applies specific to complex compounds, where you have like one central metal and then you have ligands forming coordinate bonds with this.
Okay. So, like, if you have a particular, I mean, I don't know, but just for example, if you have, say, with iodine, like any compound with iodine, and it has I6, so then you'll say 6 is the coordination number.
COI6 अगर है तो 6 is the coordination. There's more to it. Like when I do the chapter with you guys, we'll elaborate on that. Because you have like we've seen ethylene diamine, EDTA, which it is capable of forming multiple linkages, right? So we'll discuss that in detail later. But yeah, simplest thing like to follow now, yeah, 6. Whatever is in the square brackets, that's what is counted as coordination. Right. So yeah, Kaveri, you guys, should we go to the tetrahedral complexes?
Yeah.
Okay. Kaveri?
Yes, ma'am.
Okay. So concept will be the same. The only difference is in the geometry. Okay. So octahedral mein it was pretty simple, straightforward. Octahedral mein it's like 2 on each axis. X axis pe idhar udhar, y axis pe idhar udhar, and then z axis upar niche. In the case of tetrahedral complexes, where are the ligands approaching from? Okay. So tetrahedral is kind of like the opposite of octahedral. So octahedral mein it was along the axis. Tetrahedral के case में the ligands are located in between the axes. So if you remember, tetrahedron is like this, right? So it's like a weird 109 or 110 degrees angle pe hai. This is a tetrahedron. You have a triangle. It's a triangular pyramid essentially. So the ligands, you take it to be in between the axes. One of them, if you start, it's difficult to represent on a 2D this thing. So imagine horizontal पीछे इस axis के पीछे इधर in this quadrant. So if these were the three axes, you have x, y, z is like आगे पीछे. So x, y. So if z is like this way, imagine over here this area. Okay. So there's one. Then over here is another, like same thing niche, but on the front side. And then the third is over here. Upper. Like in this quadrant, like Z and Y quadrant, and then upper. And the fourth is in over here, this quadrant. So it's like 1, 2, 3, 4 tetrahedral. Okay. So in the case of a tetrahedral complex, ligands approach in between the axes. Okay, so if they're approaching in between the axes, which orbitals will be more affected? Which ones will be less affected?
Like the opposite, then the on-axis ones will have a lower energy, the x square minus y square.
Yeah. So the T2G orbitals, dxy, dyz, dxz, will have their energies increased, and dx square, y square, and dz square energy is decreased. Okay. So if we were to go with the previous notation, spherical may, yeah, it's increased. The splitting happens in the reverse direction. So the T2 orbitals have higher energy, and the E orbitals have lower energy. So the everything else, like the concept remains the same. Notation slightly different. Since we are talking about tetrahedral complexes, this splitting energy is called, it's denoted by delta T.
Miss, but what was the reasoning for them approaching between the axes?
Because tetrahedral, the shape itself is different, no? 4 different directions. So even if you oriented it over here, the other three are like somewhere in between. So the 3 orbitals that are in between the axis will get more affected than the ones that are along.
Than the one on the axis.
So again, keeping with the symmetry, the T2 orbitals increased by how much? 3 by 5, 2 by 5 of delta T.
3 by 5, delta naught, 2 by 5 delta.
डेल्टा टी है अभी क्योंकि टेट्राहेड्रल कॉम्प्लेक्स
2 by
यहाँ पे
5
भी 3 by 5 और
and नीचे वाला 3 by 5.
हाँ. So there are 3 orbitals in the higher energy thing, right? Like the total should be equal. So if this takes 2/5 of delta t, so 2 by 5 into 3 times will be equal to, by how much has this decreased? 3 by 5 times delta t.
What does delta T stand for?
Same concept. T denotes tetrahedral क्योंकि this is the difference in energy, splitting energy in the case of a tetrahedral complex.
So previous for octahedral was just delta naught.
Yeah. Because octahedral में ही you will come across that sort of a splitting where the EG orbitals have higher and that has lower. So in general, for the same metal atom ligand combination, or like keeping everything same, for the same metal ligands and metal ligand distances. So it was found that delta T, like tetrahedral splitting energy, is 4 by 9 times delta naught, the octahedral splitting energy.
Can we take a break now?
Yeah, 5 minutes left. We'll finish off tetrahedral complexes. Then by the time this meet also will be completed, take a break.
where did you get 4 by 9 from?
It was just found out like this is the relation between tetrahedral complex or octahedral complex K splitting energy. But one thing is important, it's not just the same metal, but it's also for the same metal ligand and metal ligand distances. Like keeping all the conditions same, if you were comparing a tetrahedral versus octahedral splitting energy, this was the relation.
Ma'am, how much of this chapter is left now?
Almost done. Have you guys done square planar also, geometry wise, all of this?
No.
Only tetrahedral and octahedral you have, right?
Yeah, we are still not completed. I guess it will take tomorrow's session to complete it in school. Today, ma'am was doing this only, the spectrochemical series, and she was giving some notes related to it, like
You
written.
haven't finished the chapter, but they included this chapter in your exam and excluded electrochemistry.
Electrochemistry has not been completed also. It's also left.
Oh, you
last
said
time.
different people are taking up.
Different teachers are taking up, no, that's why.
Okay. Okay. Metal carbonyls is not there according to what CBSE has sent. Let me know if your teacher has taken it up. We'll find some time to do it. Apart from that, we just have to discuss color, but color is pretty easy. Like you guys know how colored compounds happen. Just discuss a little bit about it. Done in like half hour. Okay, we will not do square planar then. If you want just for information, I can give it, but that's up to you. Yeah. So because see, for octahedral, like tetrahedral energy, like splitting energy is part of the octahedral splitting energy, right? So usually you will not find, like, because the splitting energy is so low, you will not find low spin configurations in tetrahedral as much as you'd find in octahedral. So more often than not, tetrahedral is always going to be high spin. Like, it's a usual filling up of electronic orbitals is what you need to find, follow. Okay, make a note of it. Orbital splitting energies are not large enough to force pairing. Like octahedral में strong field के case में pairing is being forced because splitting energy is that high. In this case, it's not that high. So orbital splitting energies are not large enough to force pairing. So low spin configurations are rare. They're rarely found in tetrahedral complexes. So suppose you're asked to describe electronic configuration, structure, shape for tetrahedral complex. You don't have to think so much. You can just straight away, like it's going to be low spin, you can follow the usual method only. Only in the case of octahedral complexes, you need to check whether ligand is strong or weak or like all these other things.
So in this case, it will always be low spin complex.
Yeah.
But why?
Because the splitting energy itself is pretty low.
But why is the splitting energy low?
Geometrically, it's been found that way, that splitting energy in tetrahedral complexes is found to be lower than that of octahedral. So numerically, like that's how it worked out the energies. Okay. All right. There's 1 minute, less than a minute left. So color part of it, like take like 15, not 15. It's 5:30, right? We'll meet back at what, 5:35, and then we'll discuss color. And that'll be the end of the chapter. And
Ma'am, that's only 4 minutes.
Ma'am, is it really necessary to have a 3-hour class? I mean, I don't know. I feel really sleepy after 2 hours, and then my attention span is just gone.
or we'll do one thing, we'll change up some, like, okay, we'll figure it out. We need to have 3-hour class, otherwise we won't be able to finish things in time. Either we need to increase the number of days, or how was the